Ever wondered how your computer can perform multiple tasks simultaneously? The secret lies in the heart of your computer system, the multiprocessor system. This is a type of computer architecture that employs multiple processors, also known as CPUs or cores, to perform calculations at the same time. Think of it like a team of workers, where each member is working on a different part of the project simultaneously, thus getting the job done faster and more efficiently. This is exactly what a multiprocessor system does. It enables parallel processing, allowing multiple tasks or processes to execute at once across different processors. The result? Increased computational power, improved system throughput, and enhanced scalability compared to single processor systems. So in short, multiprocessor systems are the powerhouse behind your computer's ability to multitask efficiently. Now, have you heard about Symmetric Multiprocessing or SMP? It's a principle that forms the backbone of many multiprocessor systems. In a nutshell, symmetric multiprocessing treats all processors as equals. That means every single CPU or core in the system has the same access to the system's memory and input-output resources. No CPU gets preferential treatment. But here's the interesting part. The operating system plays a crucial role in this. It's the operating system that manages task scheduling, resource allocation, and coordination among processors. It's like the conductor of an orchestra, ensuring each instrument plays its part at the right time and in harmony with the others. By running a single instance of the operating system, an SMP system can efficiently distribute tasks and resources among all processors. This results in improved system throughput, as multiple tasks can be processed simultaneously. Thus, symmetric multiprocessing ensures that all processors in a system work together harmoniously. But how does the operating system ensure that work is evenly spread across all processors? Well, the operating system plays a pivotal role in this process through the distribution of tasks and processes. Imagine the operating system as a skilled orchestra conductor, ensuring every instrument, or in this case, processor, is perfectly synchronized and utilized. This involves a technique known as dynamic load balancing. It's like a very sophisticated game of Tetris, with the operating system constantly rearranging tasks to fit them into the available processors. The goal is to make sure that no single processor is overwhelmed while others are underutilized. Load balancing is not a one-time task. It's a continuous process of monitoring, assessing, and adjusting the distribution of tasks to maintain an optimal balance. It's about keeping the workload even, ensuring that every processor is pulling its weight. In addition, the operating system also manages the prioritization of tasks, ensuring critical processes get the resources they need when they need them. Therefore, efficient task and process distribution is crucial to maximize the benefits of multiprocessor systems. So how does the operating system decide which process gets the CPU's attention first? This is where the concept of CPU scheduling comes into play. In a multiprocessor system, the operating system uses advanced scheduling algorithms to allocate CPU time among multiple processes or threads running on different processors. These algorithms, such as round-robin, priority, or shortest job next, aim to minimize CPU idle time and reduce contention for shared resources, thereby optimizing system performance. But it's not just about deciding who gets to use the CPU first. The operating system also has to ensure that all processes have access to the data they need when they need it. This is where memory management comes into play. In multiprocessor systems, coordinating access to shared memory resources among multiple processors is a critical task. The operating system must ensure data consistency and maintain what is known as cache coherence. Cache coherence refers to a consistency mechanism for multiple caches of a shared memory resource. It ensures that changes made to the data in one cache are immediately reflected in all other caches where that data is stored. To achieve this, multiprocessor systems utilize protocols like the MSI, Modified Exclusive Shared Invalid, or MOISI, Modified Owner Exclusive Shared Invalid protocols. In addition to cache coherence, the operating system also employs memory synchronization mechanisms. These mechanisms help to coordinate the actions of multiple processors, ensuring that they do not interfere with each other while accessing shared memory resources. Synchronization can be achieved through the use of locks, semaphores, or other similar constructs. So, in a nutshell, CPU scheduling and memory management in multiprocessor systems are about ensuring that each processor gets fair access to the CPU and memory resources while maintaining data consistency and synchronization. These mechanisms help to optimize system performance, enhance scalability, and ensure the smooth operation of the system. In essence, effective CPU scheduling and memory management ensure optimal utilization of system resources. Ever wondered how different processors in a system communicate with each other? Well, let's dive into that. In multiprocessor systems, interprocessor communication is key to coordination and data exchange amongst processors. Various mechanisms are employed to facilitate this communication. Shared memory is one such mechanism. It's a region of memory that's accessible by all processors, allowing them to read and write data. This shared access enables processors to exchange information and synchronize their actions. However, managing access to shared memory can be a complex task. It requires careful coordination to maintain data consistency and avoid conflicts. Message passing is another mechanism for interprocessor communication. In this approach, processors send and receive messages to exchange data. The messages are typically sent through a communication network, which could be part of the system's memory or a separate network infrastructure. Then we have synchronization primitives. These are mechanisms that control access to shared resources and ensure that processors operate in a coordinated manner. Examples are semaphores and mutexes, which are used to prevent simultaneous access to a resource by multiple processors, and interprocessor interrupts, which allow one processor to signal another processor. Now let's talk about scalability. Multiprocessor systems are highly scalable. They allow additional processors to be added to the system to meet growing computational demands. But as the number of processors increases, the task of managing system resources becomes more complex. The operating system plays a crucial role here. It must efficiently allocate tasks and processes across the processors, balance the workload, and manage access to shared resources. It also needs to maintain performance as the system scales up. This involves implementing sophisticated algorithms for task distribution, CPU scheduling, and memory management. In essence, the operating system must effectively exploit the parallelism inherent in multiprocessor systems, while providing robust support for concurrency and synchronization. It's a challenging task, but when done right, it enables multiprocessor systems to deliver high performance and scalability. Therefore, efficient interprocessor communication and scalability are integral to the success of multiprocessor systems. What happens when a processor fails in a multiprocessor system? This is where fault tolerance comes into play. Fault tolerance, simply put, is the ability of a system to continue functioning smoothly in the event of a component failure. In multiprocessor systems, this failure can be of a processor, memory module, or any other critical component. Now, how does a system achieve this? Through redundancy. By having spare redundant components in place, the system can switch to these when failures occur, maintaining its operations without missing a beat. But redundancy isn't the end-all. The system also needs to know when to switch, right? That's where error detection and correction mechanisms come in. These mechanisms constantly monitor the system, identifying any faults and triggering the switch to redundant components when needed. And what if the main component comes back online? Well, failover strategies manage these situations, ensuring a smooth transition back to the primary components when they're ready. So, fault tolerance mechanisms ensure that a multiprocessor system remains reliable, even in the face of hardware failures or errors. Let's take a moment to recap what we've learned about multiprocessor systems. These are powerful computer architectures that house multiple processors, allowing for simultaneous computations and offering a significant performance boost. They are the backbone of high-performance computing, servers, and data centers, among other demanding computing environments. One of the key aspects of multiprocessor systems is parallel processing. By executing multiple tasks or processes across multiple processors at the same time, these systems can handle multi-threaded or parallelizable workloads with ease. We also touched on Symmetric Multiprocessing or SMP, where all processors are treated equally, sharing access to the system's memory and I/O resources. A single instance of the operating system runs on SMP systems, managing task scheduling, resource allocation, and coordination among processors. Then we delved into task and process distribution. Here, the operating system plays a crucial role in distributing tasks and processes across multiple processors to maximize system utilization and balance the workload. Dynamic load balancing techniques can be instrumental in this task. The complexity of multiprocessor systems requires sophisticated CPU scheduling algorithms to allocate CPU time efficiently among various processes or threads running on different processors. The goal is to minimize CPU idle time, reduce contention for shared resources, and optimize system performance. Memory management in these systems involves coordinating access to shared memory resources among multiple processors, ensuring data consistency, and maintaining cache coherence. Techniques like cache coherence protocols and memory synchronization mechanisms are employed to achieve these objectives. Interprocessor communication is another vital aspect, with mechanisms in place to facilitate coordination and data exchange among processors. Shared memory, message passing, synchronization primitives, and interprocessor interrupts are some of the methods used. Multiprocessor systems offer scalability, allowing for additional processors as computational demands grow. The operating system must support this by efficiently managing system resources and maintaining performance as the processor count increases. Lastly, we discussed fault tolerance. Multiprocessor systems often incorporate redundant components, error detection and correction mechanisms, and failover strategies to ensure system reliability. Remember, the magic of multitasking on your computer is all thanks to the capabilities of multiprocessor systems.